in this section, we'll implement these 8 nonlinear functions. So I'll just walk you through the code. I have downloaded some libraries, and then these are the 8 functions that we're going to implement. So firstly, I'll just capture all these functions in my code to cross-verify that all these functions have been captured properly or not, for which I'll make use of symbolic math so that I can get the symbolic representation of these functions. So here are those 8. So I've defined a variable called x, and this x is going to get fed into all these functions. And so here's the list of all those 8. And then I'm going to generate a formula for all of them. So let me just run this code. All right, so first is my hyperbolic tan x. Then is my cubic function, which is 1 by 3 x cubed plus x, which is correctly captured. Then I have arctangent, which is nothing but tan inverse function, which is 2 arctan x divided by pi. Then I have an exponential function, which is piecewise. For positive values of x, it is 1 minus exponential raised to power minus x. Otherwise, it is as shown on the screen. Then I have a polynomial function, which is to the power 5, and a cube root also, cubic power also. Then I have asymmetric function, which is going to impact my positive x's differently and my negative x's differently. So it's as long as x is positive, it is going to implement a hyperbolic tan. Otherwise, it is going to implement a attenuated version of hyperbolic tan for all the negative values. Sigmoid function is a classic S-curve, very commonly used in machine learning and artificial intelligence, artificial neural networks. And I'll also use this for the distortion effect. And lastly, there's a hard clipping circuit, which is going to hard clip the signal at whenever it crosses 0.5 on the positive side and minus 0.5 on the negative side. So it's a hard clipper on both the sides. So as far as capturing of functions is concerned, it is correct. I now am going to pass numeric values into these functions. So what I am doing is that I have defined my x-axis, which is going from minus 5 to plus 5. It has 1000 such numbers between these two limits. And for cubic and polynomial function, I have defined a different x because they are behaving differently, so I want to plot them separately. So once again, I have captured all my functions here, 8 of them. And now I'm going to pass these x values to plot and to plot the response of these functions and see whether they are indeed nonlinear or not. So let me run this code. So as you can see, so here's a plot of these functions. 6 of them are here and 2 are down below. First point that you must note is that all of them are looking like a S-curve with varying degree of slopes. So for example, if you see this hard clip brown circuit here, it goes from here and then it straight away rises up and then it clips here. So it is clipping on both the sides. So anytime there's a hard clipping like that, enormous number of harmonics they get generated. And then there are smoother curves like arctan, which are very slowly with a lesser slope transitioning from here to here and then saturating on top as well as on the negative side. So this is as far as all those, indeed they're all nonlinear functions, there's no doubt about it. And I have plotted the polynomial function, which was of the 5th degree in a separate graph. Again, it is a nonlinear function. And this is the cubic function that I had used. So all of them are working fine. Now what I'm planning to do is that I'm going to pass a sine wave through these functions and see how the sine wave is behaving. So what I'm going to do is that I'm going to take I'm going to generate a 440 hertz note. If you are from music background, this 440 hertz is nothing but the frequency of A note on the 4th octave. And I am going to sample it at the CD sampling rate, that is 44.1 kilohertz. And for the signal will be for duration 2 seconds. And this is how I'm going to generate my complete 440 hertz sinusoidal signal. I'll apply some gain to it to increase its volume, and I will set the threshold for hard clipping at 0.5 as I showed in the function earlier. So here I'm going to pass this clean sine wave through all these nonlinear functions one by one, and then plot the clean signal as well as what is coming out of these 8 nonlinear functions. So if you see, here is my 440 hertz clean signal, a pure sine tone, and this is how it sounds. Very clean. It just has one single component. This is a spectrum. So it's at one line spectra at 440 hertz. So this is a clean signal, and now this clean signal is going to get passed through a hyperbolic tan. So you see what happened here. These are very smoothly transitioning peaks and troughs. What happened by passing the signal through hyperbolic tan is that a soft clipping has started to happen. Now, if you come from signal processing background, anytime there's a sharp transition like this can be equated to an impulse function. An impulse has got a very large number of harmonics, and these are flat DC components. So DC components don't contribute to the frequency component. So these are not going to contribute to the harmonic generation. But these slopes, which were very smooth, have now become very straight, causing harmonics to get generated. And this is the spectra of this particular signal. So you see there are harmonics which are now getting generated after passing through hyperbolic tan. So this is how it's going to sound now, the same clean tone. It is much sharper and having a richer harmonic component. Next is the cubic distortion circuit. Here you see that it is almost resembling the sine wave with very mild rounding off on top. So its harmonic content will not be very high because it's very closely resembling to the original sine wave. And as you can see, it has generated only a couple of harmonic contents here. So in guitar effects, it's generally called as overdrive, not distortion. And typically it is a very mild form of distortion and gives a very pleasing sound effect. So let's hear what this sounds like. More subdued. Then we have this arctan. Arctan is nothing but tan inverse. Here we have very sharp fall, rising edges and falling edges, but the tops are still very naturally rounded off. So this is again not going to generate very many harmonics. As you can see, there are only 4 or 5 harmonics that it has generated. And this typically comes from such kind of tone is generally comes from vintage amplifiers which used to have vacuum tubes. This is the tan inverse distorted signal. Now this has been passed through exponential function, and again it is very similar to arctan. Rounded edges on top and sharp rising and falling edges. And this is how it sounds. There are 4 or 5 harmonics that have got generated here. Okay, so now we come to the polynomial, the 5th order polynomial, and you see hard clipping is happening here. It no longer resembles like a original sine signal, so it's going to generate very many number of harmonics. As I mentioned earlier, these falling and rising edges can be almost equated like impulse functions, and the flat tops are basically the DC components. So as you can see that a large number of harmonics have got generated because of this very hard clipping kind of thing. This happens in effects like metal distortion, very heavily used in metal music. So this tone has bite to it, it's quite aggressive. Now there's asymmetric distortion that impacts the negative and positive side of sine wave differently. So here you see that on the positive side, this rounding off happens at a signal level of 1 volt. But on the negative side, this rounding off is happening at 0.5, which means negative get rounded off much earlier than the positive side. This is a very typical effect which signifies the behavior of vacuum tubes, triodes, pentodes, etc. The original typical Beatles sound and early classic rock is generated using this kind of waveform, and this has very rich and sweet mellow tone to it. Then we have sigmoid, a function which is extensively used in artificial intelligence. This has also rounded off the sine wave pretty well. It has generated 3 harmonics. And then we have that hard clipping circuit, which is clipping both on the positive side as well as the negative side. So you see it just hard clips the circuit on top and hard clips it below. So it no longer resembles like a sine wave. It is more or less like a square wave. And this is going to generate a lot of harmonics, as you can see here. So let's just play it. So a lot of harmonic content in this. Now this will become slightly more clear when you hear the actual chords here. So what I'm planning to do here is that I have played a clean G chord on the guitar and saved its wave file. And I'm going to now pass this clean guitar chord into these transformations and see how this chord sounds. So again, those 8 functions, and the guitar sound is being passed through them. So here is the clean sound, the clean G chord from the guitar. This is after hyperbolic tan distortion. bite to it. Then we have this cubic distortion. Arctan or tan inverse distortion. Exponential. The polynomial distortion, fifth order polynomial. This is going to be aggressive. Asymmetrical clipping. Sigmoid distortion. And lastly, the hard clipped, both positive and negative. So you can clearly hear that there are large number of harmonics in this because we have hard clipped the signal on both the sides. So I hope you really enjoyed this video and enjoyed the fascinating world of music and the math behind it. I'll see you in the next video.